Welcome to episode 4 of the Euler Project, a series in which we take the problems in the online Euler Project and solve them with Clojure, and then we take them to the max.
Sorry, I missed that. Could you say it again, please?
Episode 4 is a cute little ditty about palindromic numbers and their factors. Palindromic numbers. That sounds kind of cool, doesn't it? Palindromic numbers. Yeah, you got it. So here's the problem. Find the largest palindromic number that is the product of two 3-digit numbers. Now that shouldn't be too hard, should it? First, let's write a little function that generates a palindromic number from a 3-digit seed, right? So start with 621 and it'll create 621126. Okay, so here is the function that makes the palindrome. It's actually very straightforward. Maybe it's a little too straightforward. We start with a number n, and we're going to make a palindrome out of that number. And we do that by taking the number n and converting it into a string, which we call the prefix. And then we reverse the prefix and join all those elements back together into a string, and that becomes the suffix. And then we join the prefix to the suffix and plug that into parse int, which of course turns it back into an integer. Now, I understand that you could have some complaints about this algorithm. I mean, did we really have to go in and out of string representation to create the palindrome? The answer is, well, no, we didn't, but it works, and it's not going to get called that often, so, whatever. So next, we need to create the relevant palindromes, starting at 999999. But actually, you don't have to start at 999999 because 999 squared is only 998001, and the largest palindrome lower than that is 997799, so you could start there. But since that's just the third in the sequence from 999999, I didn't bother. So here's the function that makes all the relevant palindromes. Now, what we're going to do here is we're going to create a range of numbers that starts at 100 and ends at 999. Remember that range ends at n-1. We're going to reverse that. And the reason we reverse that is that we want to begin our search at 999999, the largest possible palindrome, right? So then we're going to generate the palindromes from those seeds. So we start at 999 to make 999999, and then we go to 998 to make 998899, and so on down the range. And that will allow us to consider the largest of the palindromes first. Okay, so with that out of the way, we can focus on the problem at hand. We need to find the first palindrome that is a multiple of two factors between 100 and 999. So this is the function that finds the greatest palindrome that's a factor of two 3-digit numbers. Now it's pretty easy to see how this works. We're going to loop through all the palindromes that we made before, so these appear in largest palindrome first. So we're going to be walking through the palindromes from the greatest to the smallest. And obviously, if that list is empty, then we return nil. And we hope we never get there. Okay, next thing we do is we find all the pairs of factors of the first palindrome in the list. Right, so we're considering the greatest of the palindromes in the list, and we're going to factor that out into all the pairs. So this will give us a list of all the pairs of factors. And then we filter that list into a list that only contains 3-digit factors. So those are the good pairs. And if that's empty, well, then that palindrome didn't work out. So we recur with the rest of the palindromes in hopes that maybe one of them would work out. But if that's not empty, if there are good pairs, well, then this palindrome must be the largest palindrome, which has 2 3-digit factors, and so we return that and its factors, and we're done. Okay, now how do you tell if a pair of factors is nothing but 3 digits? Well, it's pretty straightforward, isn't it? You just look at the 2 numbers in the pair and make sure that both numbers are between 99 and 1,000, so that's not rocket science. And how do you find the factor pairs of a number? So this is the palindrome, goes in here, and this is going to return a list of all the factor pairs. Well, okay. You don't have to search beyond the square root of n. You know why, okay? And then what we do is we go from 1 up to that square root. And remember, you increment it because range always goes 1 less. So we're going to loop from 1 up to that limit, and if the current number divides evenly into the palindrome, then we have found a factor, and the other factor, of course, is the quotient. And if we don't find that, then this number is a nil. So we're going to go from 1 up to the square root and replace it with either the pair or a nil, and then we just remove all the nils. Okay, maybe it's not super duper efficient, but I think it works just fine. And this gives us the answer, which is 906,609, which is 913 times 993. Okay, well, that was just a little too easy, so let's make this problem a little harder. Let's write it in PDP-8 assembly language.
What a terrible experience. How did we ever work this way? Why? Why did we ever work this way? Why did I want to?
The year was 2015, and I was playing around with the Lua language on my iPad using the Codia app. Codia provides a nice graphical interface reminiscent of the processing network for Java. I wrote some fun little ditties like a lunar lander game and an orbit simulator, but then a thought occurred to me. I should build a PDP-8 emulator.
Why did I ever do this? I was so happy. I was so proud. Why did I do it? Why did I unleash this demon on the world?
PDP-8 assembly language. PDP-8 assembly language.
Okay, kill the drama. Yes, I did write a PDP-8 emulator for the iPad, and I wrote it in Lua. And it's actually pretty cool. I mean, this PDP-8 emulator is very faithful to the original 4K PDP-8, right down to the sounds that the teletype and the paper tape reader punch make. So, if you want to know what it was like to program on a PDP-8, well, you can go get the PDP-8 emulator from the URL right up here. But I warn you.
Be sure and look only in the mirror. Man does not behold the face of the Gorgon and live.
Anyway, this was a much bigger project than I thought it was going to be. I mean, I tinkered that little Clojure program together in a matter of a few minutes, but the PDP-8 program took me days and days.
And days and days.
So here, just to give you an idea of what it was like back in 1968, let me show you just the barest minimums of the edit, compile, and test loop. All right, I'm about to show you what it was like to program on a PDP-8 in roughly 1968. And just to give you a hint here, the offline storage medium that we used in those days was paper tape. This stuff. We didn't have discs. We didn't have magnetic tape. We had holes punched in pieces of paper, this paper tape stuff. That was our storage medium. And so, without further ado, I'm going to show you what it was like to program on a PDP-8 in 1968. Now, if you look on this piece of paper on the screen, you see that there's a row of 4 dots. That's my test framework. And it did not end in a 0. And the fact that it didn't end in a 0 means that there was an error, and the error must be in the 5th test. So I'm going to scroll up, and by the way, this is not scrolling. This is a piece of paper here. I printed off the program, and I'm going to scroll up, and I'm not scrolling, I'm actually paging through a piece of paper, and I'm going to find the 5th test. There it is, the 5th test, testing double precision store. Something didn't work about my double precision store function. We didn't call them functions in those days. We called them subroutines. So let's go down and look at the double precision store subroutine and see what the matter with it is. Here's the D store, double precision store subroutine. And as I look down, I realize, oh my God, that DCA dargp at the very end at location 1024, that should be a DCA indirect dargp. Oh, I forgot the I. Well, okay. What I'm going to have to do now is edit this. How am I going to edit it? Well, okay. Fortunately, in our machines, the loader is kept in high memory at location 7777. So I'm going to go get the symbolic editor. Let's see, where's the symbolic editor on my shelf of tapes? Oh yeah, edit bin, there it is. I'm going to put that in the tape reader, and I'm going to run at location 7777. That's the location of the bin loader, and we're going to load the symbolic editor. Now, you can see that this tape is not going particularly fast. That's because most people who bought a PDP-8 bought it with a teletype as the only input and output device, and that teletype worked at 10 characters a second. But if you had a little bit more money, you could buy a high-speed paper tape reader. So I'm not going to make you wait through this. Let's use the high-speed paper tape reader. There we go. Now we're reading the paper tape at high speed as we load the editor. Okay. The editor is now loaded, and it runs at location 200. So I'm going to go to location 200. There we go. That's 200. And I'm going to tell it to use the high-speed paper tape reader and high-speed paper tape punch because we don't want to use the teletype for this. And I'm going to go get my source tape. That's dtefmathlib. I'm going to put it in the paper tape reader. And now I'm going to run the editor. Oh, heavens. Okay. I presume that worked. Now what I need to do is read in the first page. So I'm going to type R and then return. Oh, yes, it's reading. I should probably scroll my paper down. There's that R. You see the R? Yes, okay. It's reading in the first page. Now, you can't read all the source code into memory because there isn't enough memory, right? It's 4K. So you can only read some of the source code in. And I don't remember which page I need to read in here. So let's do this. Let's do a listing of the last few lines. Let's see. Slash equals, oh yeah, 168 is the last line in the buffer. So let's list 160 to 168 L. That'll tell us what the last few lines are. Now, yeah, you can see this is how fast the teletype would go. Let's assume that we put out the money and we bought a high-speed printer. So from now on, we're going to use a high-speed printer because we don't want to use the teletype. And now what I'm going to do is just list the entire buffer because I've got high-speed printer. Oh, heavens, good, okay. Yes, this is where my test is. So this first page is the page that contained the tests, but not the code that's broken. So what I need to do now is copy this to a new tape, and I'm going to do that by first pushing the T command in order to punch a leader. There, you see the leader came out. Good, because you always want that. And now I'm going to do the P command to punch the current buffer. Oh, yes, it halts. Did you know that computers could halt? This computer has halted. It does that just to make sure that you've gotten the punch ready. I'll make it run again. And now it should punch that first page of the source tape back out to paper tape. And the paper tape punch is a little bit slower than the high-speed paper tape reader, but not too bad. It's about 50 characters a second. So we'll wait for it to punch the first page. Now, as it punches the first page, we're going to have to remember to put a page marker at the end of this buffer. Otherwise, if we did another punch of a page, it wouldn't think of it as a page. It would merge the two. So I'm just reminding myself as I watch it punch. Oh, God. Yeah. We spent a lot of time doing this. Later on, I started using magnetic tape, but the magnetic tape was really just paper tape at high speed. So a lot of this happened this way as well. It was just a lot of waiting for I/O devices. Oh, heavens. Good. All right, now I need to mark that as a page, so that's the F command. Good, good. Now I'm going to kill the current buffer with the K command. Good. And read in the next page with the R command. All right, I'm reading in the next page, and that ought to be the code that I'm interested in. Good. Maybe it is. I don't know. Let's list it. Now remember, I've got a high-speed line printer here now. So, oh heavens, isn't that nice? No, this is the test framework. This is not the code that I need to fix. So I need to go to the next page. Fortunately, there is a command that I can use in this editor that will do the punch and the page and the kill and the read. And that is the N command. So this should do a punch. Oh yes, notice it halted the computer. So I can now tell it to go ahead. And that should punch that page. And when it's done punching that page, then it should do a page marker and a little bit of leader. Okay, we'll wait for it. And then when it's done with that, it should read in the next page. And yes, I did have to do this both on paper tape and then later on magnetic tape. By the way, the magnetic tape was a 9-track cartridge It was a single unending loop of tape with a beginning point on it. You couldn't rewind this magnetic tape. You could only send it forward to the beginning. By the way, that was not very reliable. The tape readers often misread the tape, and then you would have to send it all the way back to the beginning to try the read again. Okay, what's in this buffer now? We've read in the next page, so let's see. Let's list it. And let's see. This looks like the library. Yes, this is our double precision library. Good. And there's the dstore function. There it is. And we need to get to that DCA argp. Now, that looks like it's quite a few lines in. I wonder if we should count them. Oh, it's not too bad, actually. Let's see. That star 1000 is where it begins. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. It looks like it begins at around line 18. So let's do this. 18. I'm going to scroll back here. Okay. 18, comma 28L. Yes, that's it. Okay, and it looks like that line 28 is the one that's missing the I. Let's just do this. 27 to 30L. Yes. Okay. So I believe that's line 27, 28. Line 29 is the line I need to change. 29L. Yes, this is exactly what we had to do to find our way around. Okay. That is the line I need to change. So I'm going to change it by saying 29C, return. Now it's ready for me. Tab. Good. DCAI P, return. And now you exit this by typing Control L. Let's just check it. 29L. Yes. Okay. So now I think that's the whole thing. Let's just look a little bit more around. Let's list the whole buffer again. Yeah. Okay, there's all. I've got a line printer. I can afford to do that. You know, if you had a teletype, you wouldn't be doing that. Let's look up. A few pages of the line printer. Just wasting a little bit of paper. There we go. Yes, DCAI argp. That is what that is supposed to be. Okay, so now we should finish off the paper tape by doing another N. And it should, yes, it's going to punch, right? Okay, the machine halted. Start it up, it punches. That's good. And then when it's done punching that, it's going to read in the last page, which is just a couple of little goopy things. Good, yes, finish it off. Isn't that nice? Okay. Yeah, punch. I know, this is what we did. Right, I'm only just finishing the edit here. I haven't even begun to compile. We have not yet begun to compile. Alright, finish it up here. Come on. Yeah. Kind of amazing, isn't it? Okay, finish it up. Yeah, okay. I'm sure glad these days are over. We got good at doing a lot of other things when we were coding back in those days. We became experts at shooting rubber bands, because you use rubber bands for lots of things. put rubber bands around. Oh, look, it's done. Good, good, good. It read in that last little page. Let's look at that last little page to see what it is. Yeah, it's just the $sign. The $sign tells the assembler that the assembler is done. So we have to make sure that we do, in fact, punch that $sign. So I'm going to do another N. Good. And yes, go ahead and punch it. Yes, good. Now, I'm going to take that tape. I'm going to put it in my rack. There it is. And I'm going to rename it something like, DMath Test 2.pal. I'll name it that. By the way, we did not name things. We just wrote the names on the paper tape. So that's essentially what I'm doing there is I'm writing the name on the paper tape. And let's see. Now we're going to do the assembler. So we're going to load the assembler into memory. So stop the computer. Go to 7777. Yes, right. That's what we have to do. Turn all the switches off. Right. Go get the assembler, which is PAL3 bin. Put that in the paper tape reader and run. Now we're loading the assembler. Yes. This is what we had to do, guys. We're loading the assembler into memory. It's high-speed paper tape reader. It shouldn't take too long to load the assembler into memory. By the way, this assembler that I'm loading right now was written by Ed Yourdon. Yourdon. And if you don't know that name, look it up. All right, so now the assembler begins at location 200. We're going to make it do pass 1. We're going to go get our DMath Test 2 tape, and we're going to put it in the paper tape reader. There it is. And we're going to run. Okay, now it's doing the assembly. Okay, yeah, the assembler is running. Look at that. It reads the tape, it chunks on it for a while. Notice how it kind of sits there and it operates. The lights on these machines. You could tell a lot about what was going on by studying the lights. Now, I've got it in fast mode, right? Fast reader, fast punch, fast printer. So back in the day when I was doing this, if we heard that printer go chirp, we knew that some terrible thing had happened. So, like that. See that? Now, that was not a terrible thing. That I expected. That was a redefinition warning, and I am redefining some symbols in this program, so that's not a problem. Pass 1 is when the assembler builds up the symbol table. Doesn't do much more than that. Just builds up the symbol table and keeps it in memory. So it should print it. There it is. There's the symbol table. Now, pass 2. So we're going to tell it, the computer's halted, by the way. So we're going to tell it to do pass 2, and we're going to tell it to punch on the high-speed punch. I've got a little junk on the punch, so I'm going to get rid of that junk. And now I'm going to go get that source tape again, and I'm going to put it in the reader, and we're going to read the source tape a second time. And this time we're going to punch a binary tape. Go, baby. There it goes. It's going to punch that binary tape. It's reading in the source tape. It's punching a binary. You notice that the binary is much shorter than the source tape. You'd kind of hope that was true. The binary tape up there is in binary. That is the executable code coming out on that paper tape. Yep, that's exactly right. And this, again, you can watch that machine, watch those lights. What it's doing now is it's reading in the source code using the symbol table that it compiled to generate the binary object code and then punch it out on the tape. Yes. So this operation will take a little bit of time because, you know, these peripherals are slow and only 4K of memory. There's not a lot of space to hold things. Go, baby, go. Punch that tape. Punch that tape. Okay. Oh, just about got it. Just about got it. Okay. Okay, now I'm going to save that tape on my rack. There it is. And now I'm going to go to the bin loader, which remember is always at 7777. Good. Computer is halted. Turn off all the switches because the bin loader doesn't like any switches set. Go get the tape, put it in the reader, and we're going to load our program. Now we're loading the program at high speed. There we go. Good, good, good. Now, our program begins at location 200. Let's see if the tests pass. Let's see if the tests pass. Oh, heavens! The tests passed! See that 0 down there? That means there were 0 errors. All 5 batches of tests ran. The tests passed. I fixed the program. That is what it was like in 1968. Now, that's not what I did last week when I did this. No, I cheated. I used TextMate. Here, let me show you how I did it. So here's the source code in TextMate. This is the Euler 4 solution. I'll walk you through that in a little while. In the meantime, I'll just scroll through this. This is, much easier to edit in TextMate. And then, of course, when I've got it edited the way I want to, I save it. And then I go to a shell, and in that shell I execute a particular command. That looks like this. This moves the source code to my Dropbox. It also converts it into paper tape format. So now I can go over to my iPad. And I can go to my assets, the Codia assets, and go to the Dropbox asset and sync. And that should sync one item, which will be the Euler 4 PAL. And now I can run my emulator. And what I'm going to do is I'm going to select PAL 3 and load it directly into memory because that's a little cheat. And I'm going to do pass 1, starting at 200, and make sure that all of the fast buttons are set. I will go ahead and get Euler 4 PAL. Here it is. Put it in the reader and run. Now this is going to do the compile. You've already seen how the compile works, so that's not going to be anything new. This should compile the whole Euler 4 program. And it takes a couple of minutes to read the tape, so I still have to go through this part of the problem. At least I don't have to edit it that way, and I also don't have to load the assembler with the bin loader because I've got this nice little cheat that lets me load the assembler immediately. All right, so we're still sitting here compiling, and it does take it a little while. We've got, a fairly large program here. The little error message you're seeing are the redefines, and I have more of them in this program than I had in the other program. So don't worry about that. That's normal for this one. Okay, we're getting close to the end here. Only 1,000 characters to go. And remember, this is just the first pass. Let's see now. Here we go. Close, close, crunch, 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 and print the symbol tape. Lovely. Okay, now, pass 2. And we're going to punch on the high-speed punch. We're going to junk the gunk up on the punch. We're going to go get Euler 4 PAL, put it in the reader, and here comes the binary tape. All right. All right, now once again, we got like 6,700 characters to read in here. So it's going to take it a little while, but out comes the binary tape. This is our Euler program. This is the program that solves the Euler problem. I just wish it didn't take so long to compile. But what can you do, right? This is the reality of trying to write code on a 1968 PDP-8 and cheating like crazy with 21st century technology. I mean, we gotta cheat a little bit, don't we? But and we also need to experience at least a little bit of what it was like back then. Anyway, we got about 3,000 characters more to go. So here it comes, getting close to the end, sort of. Meanwhile, look at those lights. Look at the lights on the computer go. By the way, that's exactly what it was like. I mean, you'd sit there as a programmer, you'd watch the lights, be entranced by the lights on the front panel. Oh, yes. Okay. All right. Coming to the end. Almost there. Do. Oop. Almost. And that's it. Done. All right. We're going to save that tape. There it is. Now we're going to go to 777, right? We're going to go to 7777. That's the address of the bin loader. Turn off the switches because the bin loader doesn't like switches. We're going to take our tape, we're going to put it in the reader, and we're going to run. Now we're loading the Euler 4 solution problem. And we're going to get it done. Okay, all right, now let's run it. Starts at location 200, and run, baby, run. It's cranking. The little dots are palindromes that it's trying. Various palindromes that it's trying. Each dot is a new palindrome. Notice they're slowing down. Right? It takes more and more effort because the factors are more interesting as you get down there. And it doesn't take too long. This is just raw computation now. Raw PDP-8 computation. And by the way, I mean, I'll tell you about the multiply and divide algorithms I'm using, which are about as naive as possible. But here it goes. Oh, yeah, it's slowing down. Should come out pretty soon here. Yeah, okay. I know. Now, yeah, and this emulator runs at roughly the speed of a PDP-8S. You know, it's a slower machine, a little bit slower than a PDP-8I, a little bit slower than a PDP-8E, for those of you who know what the suffixes mean. Yeah. Oh, look! It found it! 906609, which is 993 times 913. And the machine halted. Oh, brother. I went through that cycle many dozens of times in order to get that program to work. Many dozens. So perhaps you're interested in the details of the code that I just wrote. Well, be careful what you ask for. So this is the code for the Euler 4 solution in PDP-8 assembly language. We begin at location 200. This is the main routine. This is the main loop. We begin with a seed. The seed you'll see down here is negative 999. It's negative because the PDP-8 can only increment. It cannot decrement easily, at least. So we use negative numbers and increment them, and that's how you decrement a positive number. CIA is how you take the complement of a number. It takes a negative number and makes it positive. So we get the seed. We turn it into a positive number. We call makePal. MakePal makes the palindrome. Then we print the dot. That was the source of that annoying dot that you saw come out. Then we get the maximum factor. The maximum factor you see down here is, again, negative 999 for the same reasons. We're going to be incrementing that in order to decrement it. Increment a negative number and then turn it positive, and that's a decrement. So we're going to save that as the beginning factor, and then of course what we're going to do is we're going to divide by successively lower and lower factors. That's the factor loop here, which we make sure that the factor is still greater than 100. We don't want it to go less than that. And then we get, we check to see if we are the factor of the palindrome. I'm not going to walk through all of this code here, just kind of see in general what's going on. If we did not get a factor, then we're going to go to main, and main will get the next palindrome. But if we did get a factor, then we're done. And this code here just prints the factors and the palindrome, kind of brute force, calling the subroutines that print the accumulator and the double precision accumulator. Here's the make palindrome function. This is the function that takes a number in the accumulator and turns it into a double precision palindrome. And you can look at here, you can see it's really just based on a bunch of divides by 10. We get the remainder, we divide by 10 again, we get the remainder, and that breaks the 3-digit seed into 3 individual digits, and then we reassemble that by multiplying several times by 10. You can work that out, and in the end we wind up with the palindromic number. Here's the function that determines if the factor is a factor, if the number is a factor of the palindrome, and of course that involves a double precision divide and a check of the remainder and so on. So I'm breezing through this pretty fast because I don't want to spend a lot of time talking about this. At location 1000, we have the double precision math library. We can load double precision numbers, store them, check if they are equal. We can add double precision numbers. We can complement double precision numbers. We can multiply double precision numbers. We can divide double precision numbers. Boy, you do not want to look at these functions. The algorithms here are horribly naive. You can kind of get a glimpse of just how naive right there as we just sit in a very, very tight loop, repetitively adding. Let's see. Here are the single precision math routines. Single precision divide. That's just a 12-bit divide. And a single precision multiply multiplies two 12-bit numbers together. And of course, the product can't be larger than 12 bits, so fairly limited function. Then we get into some teletype utilities at location 3000. You can print a character, you can print a digit, you can print the double precision accumulator, and that's just a brute force unwound loop that does a whole bunch of divides over and 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 over again just to get the double precision accumulator printed. Here's the function that prints the single precision accumulator, which is also a brute force unwound loop of nothing but a bunch of divisions. Okay, this is the test library. I left that in here. It really didn't have to be left in, but I did. And that brings us to the end. That is a lightning summary of the Euler problem. Look, by the way, there's 620 lines of code. Just so that you knew, right? Is that code clean? No, it's awful. It's terrible. In fact, I would go so far as to say that it's desperately bad. And I don't care. It works. And I'm not investing another second into it. I'm not going to deploy it anywhere. I don't have to maintain it. Nobody has to maintain it. I'm done with this thing. And good riddance. Those of you who follow me know that I often talk about Kent Beck's rule, first make it work, then make it right. Well, I'm not doing the second part of that, not in this project. No way. I'm not investing any more time in this thing. It took me way too long to get the thing to work. I'm not going to even think about making it right. Why? Because that environment was just so awful. Even though I was cheating with the editor, it was just so terrible. I mean, it was like trudging through quicksand or molasses or treacle. I mean, that took me so much longer than I had anticipated. But, and pay close attention to this now, that environment that you saw me slogging through, that's what I had to do in the first years of my career. Every day, that's what I was doing. I had to work in that environment. And a lot of other people did too. Is it any wonder that code back then wasn't clean? Is it any wonder that those of us who worked in that environment did not teach those who came after to be clean? Is it any wonder at all that the culture of rushing to get things done is still so prevalent? Looking back 50 years to reacquaint myself with that awful environment, it's no wonder to me at all. I mean, working back then in that way was sheer survival. Look at how wealthy we have become. We have gigahertz and terabytes. We've got screens and IDEs. We have a globe-spanning gigabit network. Our laptops and our tablets are dozens of orders of magnitude more powerful than that PDP-8. We have an immense amount of wealth. We're overflowing with capability. And yet, the survival instincts from 50 years ago still assert themselves. Nowadays, you and I have the time, the space, the storage, the connectivity, and the sheer raw computer power to be clean. We don't have to work in survival mode anymore. We don't have to behave like paupers. We are immensely rich, and we should start acting that way. We have the time, the capability, the opportunity, and the power to be clean. And in today's world, being clean is the only way to be fast. Anyway, enough preaching. I learned something else while I wrote that PDP-8 program. I learned that the algorithm that I had written in Clojure was really inefficient. The algorithm that I implemented on the PDP-8 was based roughly on the same algorithm that I used in the Clojure program that I showed you earlier. When I first got it running, it executed so impossibly slow that I realized it was going to take days to get to an answer. I also saw that there were some very simple changes I could make to get to the answer a lot faster. Now you might be thinking that if I improved the multiply and divide algorithms, it would have made it go a lot faster, and that's probably true, but there were some better ways to focus my time on the main algorithm. And this is a lesson that I had to learn the hard way over many years. The best way to improve efficiency is to focus on the top-level algorithms and deal with the lower-level algorithms later if necessary. Anyway, the algorithm that I implemented in the PDP-8, that top-level algorithm, which was based on the top-level algorithm of the Clojure program, that algorithm can be made much more efficient. For one thing, we don't need to go through all the factors. We don't need to evaluate all the conjugal pairs of factors because, as you can see, as the factors decrease in size, the conjugate gets larger, obviously. So as soon as one of the conjugates gets larger than 999, we can stop. So using the lessons that I learned by tuning the algorithm on the PDP-8, I rewrote the algorithm in Clojure and, well, this is the result. So here is the algorithm that is closer to the PDP-8 algorithm, based on the algorithm in the PDP-8 that I tuned to be a little bit faster. We begin with a loop, and the loop is going to be starting at the seed of 999. You notice the same variables that you saw in the PDP-8. The palindrome we begin at is 999999. That's just the palindrome based on the seed. I suppose I could have called make palindrome there, but since I knew, why not? And the starting factor is going to be 999. Okay, and you saw that in the PDP-8 program too. That was those negative 999s, remember. Okay, so inside the loop, if, and notice the and here, if the factor is a factor, an integral factor of the palindrome, right? If the remainder is 0, if it's an integral factor of the palindrome, and if the conjugate factor, the quotient by dividing by the factor, if the conjugate factor is less than 999, then we have found it. That is the solution, and we just return the palindrome. If we have not found it, however, then if the conjugate factor is less than 999, we're just going to try the next factor. So we're going to decrement the factor and continue looking for a factor that does divide the palindrome properly. But if it's greater than 999, then we're done with these factors. We can't go any farther. Decrementing the factor is not going to make the next one less than 999, the conjugate less than 999, and therefore what we do is we try the next seed by decrementing the seed and making the palindrome and starting the factors over at 999. Now, you could probably make some improvements on this, but this turned out to be pretty good. So here, let me give you an example of just how good this turned out. All right, we've started up a shell. Let's get a REPL going. Okay, we got a nice little REPL going. Now, let's see. Let's do the original algorithm first, find greatest palindrome. And this should run for a period of time and give us some timing numbers. Yes, okay, so that took us 9.5 seconds. Now, let's do the exact same thing with the fast find greatest palindrome. Yeah, okay, good. And that's going to run in significantly less time. It's like 20 times faster. Not quite 20 times faster. Oh, and, does it work, fast find palindrome? Yes, it does, 906, 609. Just so that you knew, right, that it does, in fact, work. So this here is significantly faster than the original algorithm that I wrote. Now, maybe that doesn't surprise you because, after all, I used the same tunings in that algorithm that I used in the PDP-8 algorithm to speed that up. So maybe you think it should have been faster, but it was surprising to me. You see, the lists in that first program are all lazy. All those functions return lazy lists, which means that we aren't actually calculating all the palindromes up front. We aren't actually finding all of the pairs of factors up front. We're actually doing them one at a time as the lists are evaluated lazily. And that means that, well, at least from my point of view, the first algorithm should not really be any slower than the second. So then why is the second algorithm so much faster? Well, I can think of 3 reasons. First of all, lazy lists aren't free. There's a bit of overhead to them, although, honestly, I don't think that's what accounts for a factor of 20 difference. Second, the first algorithm had some inefficiencies, like, the removal of the nils and stuff like that, but a factor of 20?
No, I don't think so. I don't think that was a factor of 20.
No. Third, and this one's the kicker, Clojure does not evaluate lazy lists one element at a time. Rather, it chunks them by groups of 32 elements at a time, and that, of course, could easily add up to a factor of 20. So let's try an experiment here. Let's force the worst case by making all the lazy lists non-lazy. And you do that by putting a do-all in front of them. That just completely evaluates the lists all the way out to their ends. And so there's nothing lazy going on here. And when I do that, and when I run that timing, well, it takes an extra second. So it's a little slower. Now, if we're doing that in batches of 32, maybe that makes sense, right? Maybe because there probably aren't very many items in those lists. And so maybe that makes sense. Maybe. Yeah, well, maybe. So let's see what happens if we try to find the largest 8-digit palindrome that's a multiple of two 4-digit numbers. So that's really easy to do. I just changed the make palindromes function to go from 1,000 up to 10,000 and checked that the factors were between 999 and 10,000. And for the faster algorithm, I just changed all the seeds to be 4-digit nines and the palindrome to be an 8-digit set of nines. And that's really all there is to it. Notice that I left the do-alls in, so this is going to be really inefficient. There's not going to be any laziness in the original algorithm. And here's the result. You see that down here. First of all, it does find the palindrome. It's 99000099, which is the product of 9901 and 9999. And it took it 103 seconds to figure that out. Then I did that with the faster algorithm, and it took half a second. So there's very clearly a huge difference between these two algorithms. And just in case you were worried, yes, the faster one does in fact find the proper palindrome. So let's pull those do-alls out of there. Which I can do, by the way, by going to the next revision. There we go. All the do-alls are out. Let's go back to the REPL. Okay, we're going to load that up in the new REPL, and we're going to try that one last time. Let's see, that's the right one. We're going to use the original algorithm with laziness. This one will be lazy. Well, 96 seconds as opposed to, what was the other one? 103 seconds, not really a huge difference there. Certainly not a half a second. So what is the lesson here? I guess the best lesson is don't count on lazy lists to be a huge efficiency improvement. It worked an awful lot better when we didn't use the list at all. So, okay, all right, maybe that is the lesson here. The last thing I think we ought to do in this episode is to play around with the factors of palindromic numbers. So I brought our old friend, the factors of method from the last episode in here, and I thought we'd just find the prime factors of some palindromes. So here, I make palindrome into a range of numbers from 100 to 200, and you can see we do in fact get reasonable palindromic numbers in that range. So that much is working, and we kind of knew that was working anyway. So next thing is I compose factors of and make palindrome right there, right? And I pump that into a map of range 100 to 200, and out pop the prime factors of each palindrome. Now, this is pretty interesting because there's an 11 in every one of these. 11 is a factor of palindromic numbers that are made this way. Now, I'm going to characterize these as a special kind of palindromic number. They have an even number of digits. There are palindromes that have an odd number of digits. In fact, here's one right there. That's a palindrome with an odd number of digits. And, oh, here's another one. Look. Oh, and there's one 1, 2, and oh, there's one. Look, there's one down here. It turns out that 11 is a factor of every palindromic of even length. And very often, the palindromic of even length is a multiple of 11 and a palindrome of odd length. That's pretty cool, isn't it? I mean, look at all those 11s. Now, by the way, it's not hard to prove that 11 must be a factor of a palindromic number of even length. That is not hard to prove. Here, I did a larger batch of them. And what I find interesting in this larger batch, is that there's this range where all of a sudden you get these massive powers of 2. And that seems to be prevalent throughout here in this range of palindromic numbers. Lots of powers of 2 with, of course, an 11. And you'll see lots of odd palindromes as well. There's an odd palindrome. Oh, sorry. There's an odd palindrome, and there's an odd palindrome. Well, as we keep on going down, you'll see more and more of this with all these powers of 2. Look at these powers of 2, these massive powers of 2. I don't understand that at all. I just think it's very interesting. There's another one of these massive powers of 2. Okay, we just keep on going and going. And of course, you see, as we go down, there's these odd palindromes as well. Odd palindromic numbers. If I can get my thing to work out properly. Okay. And so I thought, well, let's try 8-digit palindromes. So I went from 1,000 to 2,000. That'll give us a bunch of 8-digit palindromes. And of course, 11 is still everywhere in there. And we still see, odd palindromic numbers, or palindromic numbers of odd length, I should say. They're fairly frequent, as long as they're multiplied by 11. And there's not as many powers of 2 in this batch for some reason. I don't know why. We don't see those long runs of 2s in here. But the 11s are everywhere, of course. And, you do find the occasional odd palindromic number of odd length. And numbers that are almost palindromic, but not quite. That's like an almost palindromic number. Not quite. There's an interesting palindrome of odd length. So, I don't know what to tell you about this. It's easy to prove that 11 is got to be a factor of a palindrome of even length. But the other stuff, well, I'll let you work on that. Anyway, that's Euler 4. A fun little jaunt through palindromic numbers and PDP-8 assembler. I hope you enjoyed yourself. I hope you learned a thing or two, even if you learned that you really are glad you're not programming a PDP-8 in 1968. But you're not going to want to miss the next exciting episode of the Euler Project, where we tackle multiples of consecutive numbers.